unlocking the power of recombinant innovation. Now, wandering around Chicago in 1912, William Klann was a man on a mission. He was part of a team set up to explore ways in which they could reduce the costs of manufacturing a car to fulfill Henry Ford's vision of a motor car for the great multitude. They'd already developed many of the ideas behind mass production: standardized and interchangeable parts, short task cycle work, specialist machinery. But what Klann saw while he was walking past the Swift Meat Packing Company's factory gave him an insight into a key piece of the puzzle. The workers were effectively disassembling meat carcasses, stripping off various joints and cuts as the animals were fed past them on a moving overhead conveyor. In a classic moment of insight, bing, he saw the possibility of reversing this process. And within a short space of time, the Ford factory boasted the world's first moving assembly line. Productivity rocketed as the new idea was implemented and refined. Using the new approach, Ford was able to cut the assembly time for a Model T to just 93 minutes. Not that those meat packers had invented something new. Way back in the early 16th century, the Venetians had already developed an impressive line in mobile assembly. By moving ships along canals in order to fit them out for battles, they were able to produce, arm, and provision a new galley at a rate of 1 per day. Now, 40 years after William Klann, Ray Kroc was running the hamburger business originally established with his friends, the McDonald brothers. Now, he was looking for ways to improve productivity, and so began applying Ford's assembly line techniques for making cars to making hamburgers. The rest is fast food history, with the company now selling more than 75 hamburgers every second and feeding 68 million people every day. A little later, and in another part of the world, Dr. Govindappa Venkataswamy retired. He'd worked for many years as head of ophthalmology in the main hospital in Madurai in India, and he decided to use his expertise and his newfound free time to try and help prevent blindness in rural communities in his home state of Tamil Nadu. He was focusing particularly on the challenge of cataract surgery, removing the cataract that grows over the lens of the eye and then replacing that with an artificial lens and making sure it doesn't get infected. Sounds simple, but it's quite complicated. In particular, while the treatment itself is well developed, it comes at a price. In an Indian hospital, the cost works out at around $300. And in a country where most people, especially in rural environments, earn less than $2 a day, such a price tag puts treatment out of reach. So in order to achieve his dream, he had to search outside the conventional health sector, seeking ideas from other worlds with similar challenges. Specifically, he was looking for low-cost ways of carrying out activities systematically, reproducibly, and to a high-quality standard. And eventually, he found his inspiration under McDonald's Golden Arches. He saw the underlying similarities in the core processes which they were using and adapted their principles of assembly line manufacturing to the context of eye surgery. Developing and refining what became known as the Aravind system has meant that the average cost of a cataract operation is now $25, and over 60% of patients are treated for free. Now, this isn't done by compromising on quality. In fact, the Aravind hospitals have better performance than many Western hospitals. Aravind has become the world's largest and most productive eye care service group. It's responsible for treating over 35 million patients with this low-cost, high-quality model. Now, what these stories have in common is that they're working on the same problem, but in a different context. And this is a powerful resource in innovation. answers don't always have to be new to the world. They can also be adapted from different contexts, what we can call recombinant innovation. It's not a new idea. Thomas Edison was an early and active exponent, seeing the possibilities in drawing on many examples of proven technology and reapplying them in different fields. His invention factory in New Jersey offered the world a minor invention every 10 days and a big one every 6 months, and it largely succeeded. Think about the problem of turnaround time. Now, in the low-cost airline world, much depends on being able to land a plane, disembark the passengers, clean and refuel the plane, load new passengers, and take off again in as short a time as possible. Turnaround time. Southwest Airlines still holds the record for this, regularly managing turnarounds in well less than 20 minutes. But this isn't just an issue for the airline industry. It's a version of a problem facing many others. For example, in hospitals, it's the challenge of using an expensive resource like an operating theatre as efficiently as possible, swiftly moving out post-operative patients, cleaning, sterilizing, preparing, getting started on the next patient as fast as possible. Now that's got a lot in common with a very different world. Fans of Formula One racing, motor racing, will know that a slow pit stop can ruin a driver's chances in the unforgiving world of Grand Prix motor racing. But all of these are variations on the same basic theme. And importantly, the solutions developed in one world can be adapted and applied elsewhere, just as Dr. Venkataswamy found with Aravind. Back to car manufacturing. Turnaround time was a major challenge in the car industry, where the concern, particularly when you have different models, to reduce the setup and changeover times of the huge body presses led engineers at Toyota, under the direction of Shigeo Shingo, to develop the single-minute exchange of die, SMED approach. Essentially, this approach enabled reductions from several hours to set up a press to less than 5 minutes. SMED principles underpin the turnaround revolution in the airline industry, the success of Ferrari's record-breaking team on the racetrack, which can carry out a complete pit stop in less than 6 seconds, and in many other places. In fact, it's not a one-way process. Part of the power of recombinant innovation is crossover learning through sharing different experiences of dealing with the same basic problem. In a recent visit to the Great Ormond Street Children's Hospital in London, where they were trying to learn about pit stop turnarounds from Ferrari, the Ferrari team not only delivered important insights to the hospital, they also took back some new ideas to apply on the racetracks of the world. Now, recombinant innovation has a number of advantages. In today's innovation landscape, it's seen as a powerful opportunity. Why waste time developing solutions from scratch when you could adapt and modify a proven model from elsewhere? The approach offers a number of advantages. It reduces learning costs, since much of the original development of an innovation has already been undertaken in a different context. So there's still a need for local adaptation, but there's a chance to adopt an innovation further up the learning curve and with lower risk. It opens up new and different innovation search space by moving the focus to outside a particular area. If you like, getting out of the box. In doing so, we can establish a new trajectory for further innovation. For example, the Aravind model of safe, low-cost healthcare has been applied to perinatal care, elective surgery like knee and hip replacement, even heart bypass operations, all with similarly dramatic results. And recombinant innovation also opens connections to new networks, effectively enriching the gene pool of ideas which organizations can draw on and enabling further open innovation connections. But recombinant innovation doesn't just happen. Exploiting these opportunities requires building new capabilities. In particular, we need abstract-driven search. To find analogous solutions in different worlds, we first need to climb a ladder of abstraction, to look down on them so that we can see that they're actually the same problem being solved in different contexts. And this is essentially about translating or reframing the problem. When Wolfgang Dirichs, a research chemist at the German company Henkel, boarded a plane in 1967, he didn't expect to be getting off with a radical innovation in the stationery business. But when he saw a woman applying lipstick, he began to see a connection between this and the possibility of selling glue, not in messy pots or tubs, but as a stick. Pritt Stick was the result of that flash of inspiration and has since sold over 2.5 billion units in over 120 countries around the world. But we also need brokerage, finding different ways to link different worlds. The danger in abstract-driven search is that the level of specification can be so abstract that the potential connections are not spotted. We need both the ability to make connections across very different fields and to see a fit between needs and means. Now that's a role that Thomas Allen, in his pioneering work on innovation in the United States space program, called the role of the technological gatekeeper. And it's something which Procter & Gamble, in their Connect and Develop open innovation journey, have called the technological entrepreneur. Effectively, people, brokers who enable connection. But for recombinant innovation, we also need cyclic adaptation. Jumping between two worlds offers new insights and innovation solutions, but it's not a simple matter of plug and play. Significant adaptations needed to turn the principles from one world into practices in another, and essentially involves a series of prototyping cycles, configuring to local circumstances. It's effectively the reverse of that abstract-driven search process, moving in this case from that high level of abstraction down to a particular application in a specific operating environment. Now, James Dyson famously saw a link between industrial cyclone technology and a new design for the domestic vacuum cleaner. But it took him some 5,000 prototypes and 5 years to come up with the one that worked. Now, organizations grow through what they know, and using external knowledge is a critical capability. But it doesn't just happen. Organizations need to develop their absorptive capacity to find, assimilate, and deploy that new knowledge. Part of that story is learning to reframe and recombine, and it's one that is rich with possibilities.